Swayam Prabha. Digital India. Educated India.
Let's move on to the next presentation. The presenter will be Abhilasha Masewali, right? I'm so sorry for that. Yeah. And the title of the talk will be Integration of Supply and Demand Side Management. Then optimal energy storage design incorporating the effect of uncertainty. Please start if you're ready.
Thank you for giving me this opportunity at speaking at PSC. So very good evening to all the audience online and offline here. I'm Dr. Abhilasha Maheshwari from IIT Jodhpur, and I'd also like to introduce my co-authors in this work who are not in person present here. So he's Dr. Shamik from IIT Tirupati and Professor Goody from IIT Bombay. So the title of my talk today is Integration of Supply and Demand Side Management for Optimal Energy Storage System Design, Incorporating the Effects of Uncertainty. So as we all know that manufacturing industries are the most energy intensive industries, and the major part of the operational expenses in these industry comes from the electricity cost. So these industries need to adopt to energy demand side management in order to minimize their operational expenses in the overall system. And therefore, there is a strong need of energy demand management in all kind of manufacturing industries. For example, steel making, cement production, air separation, or chloralkali, etc. So this is also important because of the high volatility in the electricity prices in which these industries pay to the power grids, as well as the demand response, which is like the operational flexibility of the plant is there, which can be exploited to take the advantage of the time-sensitive electricity prices. So as you can see in this figure, the electricity prices are at 3 levels usually, the low, medium, and the high ones. And the production of the industry, any industry needs to be scheduled in such a way that they optimize their production so that they have the minimum energy costs in the production process. But the major challenge in this is that this load shifting has to be done very carefully because the customer demands need to be satisfied, and also the process constraints at all the times. So this is one of our work where we have done this production scheduling, and this is so the major constraints in this scheduling model for any energy demand side management are allocation constraints, transition constraints, mass balance constraints, capacity constraints, demand satisfaction constraints, and energy balance constraints. And the main objectives are minimization of cost or maximization of profit. The typical decisions that an industry seeks are optimal production schedule for the plant, optimal inventory profile for their material storages, and the product demand fulfillment. So in this paper, we have actually taken an air separation plant as a case study where we have gaseous products and liquids. So gaseous, oxygen, nitrogen, and argon, and liquid oxygen, nitrogen, and argon are the products. And the raw material air is free, but the major cost of the production is electricity cost. So the gaseous products in these cryogenic air separation plants are usually demand of the ancillary plants like steel plants. So they are directly catered using pipelines, but the liquid products like liquid oxygen or liquid nitrogen, they are supplied to on-spot demands to different customers via delivery trucks. So in this previous work, we tried to do this demand side management, and as you can see from this plot that corresponding to different electricity cost levels, the production profile was optimized to a bit, and this is like the schedule of different process operations that are in their air separation plant. But still, if you can see at some moments, the production profile is during the peak hours of the electricity consumption like this. So is there a way to further improve the decision-making processes in such cases? And for that, the other aspect comes as of liquid product utilization. So the liquid oxygen and the liquid nitrogen, which are usually stored in the plant and being catered to the on-spot demands, there is a other way that it provides additional operational flexibility in which the industries actually dry-ox the liquid, which is converting it back to the gaseous product, and then using it for electricity production. So this was also being done in our previous work by Mishra et al. And you can see that there is a reduction of 3.2% in the power cost with only grid power and only grid power with liquid utilization model. But still, this is all about the demand side management. Is there a further way to improve the decision making? Because still you can see at some peak points the production profile is still at the peak of the demand fulfillment. So basically this production profile is still dominated by the demand satisfaction. So the next aspect comes as the integration of both the supply and demand side management in this aspect. And here what has been done is that the supply side, that is the energy supply side, is being integrated with the demand side management. So on supply side, there are all the three things. Since nowadays industries are becoming more green, are trying to becoming more green in nature, they are involving more renewable energy sources into their systems. So they have this solar concentrators, the wind energy, and also the deterministic cogeneration systems like membrane-based fuel cell systems, and battery storages to store the energy from solar and wind energy. And in addition, they do have power grid also. So this is a kind of a hybrid energy system that industries are planning to, most of the industries have done, and some are also planning to do this. But there needs a strong integration between these two, supply and demand, to optimize the production scheduling so as to minimize the total energy consumption. And you can see that further from 3.2, with this addition of supply side, in our previous work, we could the results showed that there is a further reduction of 20.7% in power costs during with this energy mix supply side model with liquid utilization. So this was the motivation of doing this, but this was all of our deterministic optimization, considering that solar energy, the wind energy, and fuel cell all have a deterministic output amounts. So in this work, we further on carried on to incorporate the uncertainty effects, and the major impact comes on the lithium-ion battery storages. So as we all know, these batteries are quite capital intensive, and it was like around 35,000 rupees as per kilowatt hour, the current cost in Indian scenario. So from this deterministic result set, you can see that until the cost of this battery systems decreases to 10 times to 3.5, they are not feasible to install into the plant in terms of their capital expenses. Therefore, the efficacy of energy storage, but this is again based on the deterministic results. So we want to exploit whether considering the uncertainties would impact this decision of battery size as well as battery installation. Therefore, the efficacy of energy storage should be discerned considering the uncertainties related to the renewable power generation. So that is where this integration again comes into picture with the uncertain impacts of solar and wind energy as well as the uncertainty in the demands. So the demands are also uncertain, and the solar and wind energy are also uncertain. Further, there is an augmentation of cryogenic energy storage, which is already present in the air separation plants. But the trade-off is that its energy conversion efficiency is very low, which is just around 50%. But the benefit is that no extra capital cost is required. So we have included that energy storage as well in the model. So now we have battery and cryogenic energy as a storage system in the model, and the solar energy and the wind energy and power grid as a supply sources. So the need for uncertainty is because of these two parameters, the renewable energy and the demand data. And the popular solution methods, as we all know, for incorporating uncertainty into production or optimization models is stochastic optimization and robust optimization. However, we also tried for stochastic optimization the most classical method, like two-stage stochastic programming with recourse approach, but it has become intractable for the problem size like this. So in this work, we have tried these two approaches, the stochastic simulation optimization and the scenario-based robust optimization. The key idea of stochastic simulation optimization, which I'll refer from now on as SSO, is to solve a deterministic problem for each scenario set and then calculate the weighted average objective function. Whereas the scenario-based robust optimization is an efficient way of dealing with the uncertainty in terms of the worst case of all the realization of that uncertain event. So in the results, first we have done a convergence analysis to identify an optimal number of scenarios that should be constructed to appropriately define the uncertainty set, and in the range of 0.5% fluctuation, we get that number as around 250 scenarios. So further, for analysis, we chose 250 scenarios as an acceptable number of scenarios for solving the proposed model, and both SSO and RO was used for these number of scenarios. The second, so the first comparison that was made in the paper is about SSO versus RO. That is, which method is better, simulation-based stochastic optimization or the robust optimization. So as you can see that in the results of robust optimization, the major chunk is coming on the target inventory violation, penalty factor basically. Whereas in the SSO, the major chunk is from the power sale revenue, this blue one. So if you can see on the figure in the rightmost, the results of robust optimization RO, basically it is taking 90% contribution from power grid, and only around, I should say, less than even 1%, less than 10% contribution is from the wind and solar energy. So it is basically assuming that in the worst case, there is no power available from the renewable sources, and therefore the maximum power consumption is from the power grid. However, in the SSO, the minimum power grid consumption is 60%, and rest of the contribution is from both the solar and the wind sources. So scenario-based robust optimization has tried to satisfy all the scenarios, and therefore it always assumes that the worst power generation value, which is very minimal at all time points, and therefore there is a more violation at the target inventory side also, which I'll also explain in next slide. And this has increased the dependency on the deterministic power grid sources using the RO model. But if we see this thing again in the figure on the left hand side, if we see the liquid inventory profile, which is given by this orange line, so we see that in SSO model, the liquid inventory is quite maintained at the at the level of the target values, whereas it is only 30% in case of the RO model. So this yellow part, which is spot sale revenue, this is being utilized as an opportunity cost by SSO, and therefore the revenue, the power sale revenue has increased in the SSO model. So in summary, due to unavailability of adequate power, the robust optimization is using the dioxin option, which is basically draining the liquid inventory and then converting it into gaseous form and using it as an energy source. But it is not, and because of that, it is not able to cater to the on-site customers which come for the liquid demand. And therefore, it ignores the high revenue opportunity sales. And the second aspect to see here is cryogenic energy storage versus lithium-ion battery. So here we have compared the battery size for different cases. So there is one case is that there is no battery at all in the plant. There is no battery energy storage system. The second case can be a mean battery size, which means if we take the average of all the uncertain demands and uncertain energy sources, then what is the deterministic mean value of the battery size? The third one is this SSO battery, which is battery size from the SSO solution. Fourth one is the battery size from the robust optimization solution. And fifth is the maximum battery size, which is maximum size of battery in all the 250 scenarios of SSO. So if we see the battery capacity and the objective function, this plot, we can see that the SSO model, the stochastic simulation-based optimization model, provides a 22% reduction in overall cost from the no battery cost, and a 1.6% reduction compared to this mean case, which we call as the value of a stochastic solution. So this SSO solution is much better than the robust optimization. And when we compare the trade-off between CES and battery, the cryogenic energy storage and battery storage, we can see that CES was already low. It was around 17% in no battery case. But when we have a battery storage system in place, its contribution to the overall energy consumption further decreased. So it is clearly evident from all these results that lithium-ion battery is more suitable choice for energy storage systems despite their high capital cost, which was a result from the deterministic solution. And we can also see the effects of this energy storage on the power consumption, which was the point from where we started. So we can see that in no battery case versus SSO and RO solutions, the change is only of this power grid consumption. So we could get 4.5% reduction in the total power consumption using the SSO size battery from the no battery case. But there is a minimal, we can say 0.7% when we compare the SSO and RO solution battery sizes. And further, the power consumption at 3 different levels of electricity pricing, the low grid price that I mentioned in the first slide, and the mid grid price and high price, which is at the peak hours of energy consumption. So we can see that in the low grid price, the formulation is giving the same value of power consumption from all the 3. But in the mid-grid and high-grid, it is optimizing using the battery systems as compared to the no battery system. So the presence of battery is not only helping in reducing the consumption of the grid power, but it is also helping in augmenting the production profile according to the time of using power pricing. So whenever there are peak power prices, which is high grid price, we have this coming into picture, the battery storage systems compared to the low grid price when we can just utilize the power consumption from the normal grid. So in summary, the idea of integration between demand side management and supply side management for energy in the presence of uncertainty was proposed in this work. And energy storage systems such as both the lithium ion battery as well as cryogenic energy system were evaluated. And it was found that SSO provides a better overall estimate of the required size of the energy storage systems when uncertainty impacts are considered. And the results also show that integration of this kind of energy storage not only increases the reliability on renewable power generation, but it also reduces our consumption from the grid, which is to become more greener and to become more sustainable. And the presence of any ESS system will also help in better augmentation of our production profile. So it generates an appropriate optimal production profile according to the time of power prices. And the proposed methodology is a systematic framework for finding the required size. So we can also estimate the capacity of the battery which needs to be installed integrated with in-house renewable power generation systems. So thank you very much, and I would be happy to answer any questions or take any comments on the work.
Thank you so much. So, but we have very limited time, so I'm gonna take one or two very short, quick comments or questions. Do you have? Yeah, please.
So when you say uncertainty, so do you mean variability? Because uncertainty, so you're saying you're considering uncertainty in
solar and wind and demands.
Yeah, so let's say I'm at a particular time instant, let's say it's 8 a.m.
Yes.
So uncertainty would be I can have DNI or solar irradiance. I'm talking about solar irradiance.
Yes.
It could be 8 or 10.
Yes, it depends on the day. So today it can be 8, but tomorrow it can be 10. Tomorrow sun can be more brighter. So we are doing this scheduling over a time horizon. In this work, we did it for 15 days. So that's why daily there is a variability in the availability of solar power.
Okay, so today and tomorrow are different.
Yes.
In that sense, there is an uncertainty.
Yes.
At a particular time instant, there is an uncertainty in irradiance.
In irradiance. And similarly, demands are also uncertain, liquid products especially.
Okay, thank you.
Thank you. So let's listen again to the speakers.
Thank you.